Hi, my name is Stefan Zeglen. I'm a forest pathologist for the coast area for the British Columbia Ministry of Forests, Lands and Natural Resource Operations and Rural Development. Today I'm going to talk to you about creating operational adjustment factors using a specific example of a factor that we developed for root disease on the BC South Coast. So, what are operational adjustment factors? First, a little background. The primary growth and yield model used in BC for timber supply is TAS, the Tree and Stand Simulator. As you might guess, it's a bit of an overly complicated model and not meant for everyday use. So the modelers have derived another submodel called TIPSY, the Table Interpolation Program for Stand Yields. This model basically takes a range of yield tables from TAS and, based on initial stand characteristics provided by the user, creates a yield projection. OAFs are applied to those potential yield projections to reflect the reality of the operating environment. So basically a net down to the yields. There are two types of OAFs that are used in BC, OAF1 and OAF2. Apologies to Dr. Zeus. The OAF1 that we use in BC basically represents abiotic factors, so gaps in stands primarily, where trees aren't growing for whatever reason. The default value for this OAF is 15%, and it's applied consistently across the yield curve, so it nets down the projected volume by 15%. This value may be adjusted up or down based on arguments that the user can use to say my gaps are less or my gaps are more, but the default is 15%. OAF2s represent endemic biotic factors, things like decay, waste, and breakage, cull factors, and other things that would basically be used to net down the total volume in a stand. The default value for these is 5%. The effect on the yield curve, though, is different than an OAF1. The OAF2 basically accelerates starting from 0 at year 1 to its full value at year 100. So it acts differently on the yield curve. The other thing is this is mostly for endemic pests. It doesn't apply to specific insects or diseases unless you create one specifically like we have for root disease on the BC coast. Here I provided an example of how the OAF1 and OAF2 adjust the yield curve in differing ways. The graph on the right illustrates, using the dark line, the model's base case scenario. Based on user input, this is the projected yield for the conditions given. The darker dashed line is the OAF1 representation, here set at 15%, and it provides that constant net down to the yield curve over the entire curve. The OAF2, though, acts differently in that, although in this case it's also set at 15%, that 15% value is only realized at age 100. It's less before and more after. So for example, by age 150, it's actually a 22.5% net down. So that's why we create OAFs, basically to inject some reality into the model, to take what's happening on the land base and to somehow put it into the timber supply data package in a usable form so the modelers can adjust the model. The chief forester then makes an informed decision based on what's actually happening on the land base. How do we create these OAFs to reflect that reality? Well, OAFs aren't the only thing that we use. We do have unsalvaged loss factors that we calculate as well, but those are usually fixed values. The OAFs are more dynamic because they're built into the model and can be adjusted depending on the scenarios you have, the species you're modeling, and the different stand characteristics that you're trying to project. As an example of how we created and use OAF2s, I'm going to use the specific example of root diseases of Douglas fir on the south coast of BC. A little background to this. The primary root diseases of Douglas fir that we deal with are Coniferporia sulphurascens and Armillaria ostoyae. Coniferporia, for those of you who may be of an older vintage, used to be called Phelinus wirii, and I'll use that term Phelinus to identify it for the rest of the talk. Armillaria is fairly widespread and quite common in Western North America. To a lesser extent, we do have some heterobasidian occidentale and also a couple of other minor root diseases that will infect and kill Douglas fir. But for the most part, they don't amount to very much. So we're not going to deal with them in this exercise. I'll give you the punchline right now. The OV2 reduction is 7.5% in addition to the 5% default. So this results in a 12.5% reduction in the CDF-MM and CWH-XM1 and 2 subzones for all Doug fir leading analysis units. So the OV2 for root disease on the south coast was derived two different ways. The first way was done by Jeff Beal back in the late 1980s, where he looked at Doug fir leading growth and yield plots that were established in the CDF and CWH XM1 and XM2 subzones. You can see those subzones on the map to the left. The shaded areas indicate the extent of those subzones along eastern Vancouver Island and the mainland Sunshine Coast. 215 plots were used in Jeff's analysis, provided by the timber companies Macmillan Bloedel and Canadian Pacific Forest Products, neither of which exist today. These plots were originally established from 1955 to 65 as part of those timber companies' growth and yield programs in 30 to 40-year-old stands. So by the time Jeff got around to looking at them, they were already about 55 to 70-year-old stands. The plots were installed also in an era where root disease wasn't really recognized very well by people working in the woods. So the plots were placed without regard to root disease, usually in areas where they were trying to establish good growth and yield plots with no obvious interference from any kind of pest problems. So there shouldn't be a bias towards how much root disease was in these plots when they were established. Generally, growth and yield sample plots are too small to assess root disease dynamics very well because you're not going to get a lot of neighbors close by and you obviously can't tell what's happening outside the plot. So Jeff solved that issue by overlaying 139 1-hectare grids over where these permanent sample plots were placed. Each of these grids consisted of 25 50-meter square survey plots laid out on that grid. These survey plots are equivalent to roughly the 3.99 meter radius silviculture plots that we use today. Jeff collected tree data, ecological, soils, and disease data for each of the grids. So when you're looking at the example provided by Jeff on the left, you can see the square PSP growth and yield plot, and also the PRRC, are the primary root rot centers that Jeff mapped out from his survey based on the grid that he overlaid. He used the growth and yield data, though, provided by the PSP plot owners so that the growth and yield data would be suitable for use in the model. So for his thesis work, Jeff spent a lot of time grubbing around looking at root disease within these permanent sample plots and the sample grids around them. He found that 87% of those 139 sample grids had root disease. This we'll call the incidence of root disease in Doug fir leading stands within these subzones. Now the impact of those root diseases on tree volume within those plots and stands varied. Jeff came up with a range of 8.25 to 8.86% volume reduction at age 80. For simplicity, because the timber supply review breaks things down into analysis units, primarily Douglas fir leading stands, I took the 8.86% value, multiplied it by the incidence factor, and came up with a 7.7% reduction that could be applied to those Doug fir leading analysis units. So our second approach to creating a root disease OV2 for the South Coast came in 1999. We looked at the results of Jeff's thesis and wondered if we could somehow confirm his results. So we examined 39 ministry growth and yield plots 30 years after they'd been established. All the plots were again in fir leading stands at least they were fur leading in 1969 when they were established, and they were all in the CWH XM1 subzone of the Sunshine Coast. The plots, because they are growth and yield plots, are fairly limited in what we can do, so we couldn't grub around and dig things up and cut things down. But the obvious indicators of root disease were pretty easy to pick out, so it didn't take us very much effort to determine which trees were infected and which ones weren't. The table on the left gives the percent volume reductions attributable to the two primary root diseases found on the two most common hosts within those growth and yield plots that we looked at. Looking at the Douglas fir, 8.27% of the volume on those 39 plots was infected by root disease. There also was some incidental infection by other root diseases like Heterobasidion on some other hosts, but because these were very fractional in nature, we disregarded them. We also disregarded the root disease occurrence on western hemlock, since Phelinus is almost always only found on western hemlock when it's mixed with Douglas fir. So we concentrated our assessment just on Douglas fir, assuming that we'd be capturing some of the western hemlock mortality as well. So we took our volume reduction result and applied the Beal incidence factor of 87% to the 8.27% to get a 7.2% reduction for fir leading analysis units in the CWH XM1 on the Sunshine Coast. This number is similar to the 7.7% value found by Beal. So we split the difference and rounded it down to 7.5, and this is the value that we recommend that the timber supply modelers use in coastal TSRs when using Doug fir analysis units in the CDF, MM, and CWH XM1 and 2 subzones. So in conclusion, we were fairly lucky in that through two different approaches, we managed to come up with a more or less similar value in both cases. And we're able to apply that to root disease for the South Coast. Now, is that way of deriving an OAF or even the creation of an OAF the best way to account for root disease or any pest loss in timber supply reviews? Well, that's a good question. As you can tell, creating an OAF is not a trivial exercise for most pests. In fact, we tried to continue the work we started on the Sunshine Coast to try and expand it to more subzones, but we're quickly limited in the fact that if we relied on growth and yield PSPs, we had to accommodate the remeasurement cycle put together by the inventory people, and that ran into some problems. So we were never able to get a sufficient sample in many other subzones to be able to see whether we could expand the OAF2 into more areas of the South Coast, into more ecological subunits, and even applying it to more different species. That is something that we could pick up and try to continue in the future. The OAF, though, may have limited utility outside the specific use with Tipsy. Can you actually use something like this OAF, a net down factor, whether it's a fixed or variable one, in a model other than Tipsy? Submodels, like the Western root disease model that's used with the Forest Vegetation Simulator in the US, GRIM, the gall rust model that's being used in TAS for Western gall rust, and others may be likely better approaches to take when modeling pest problems, because they're looking at them specifically in how they interact with their hosts, how dynamic they are within those stands. Incidence and severity are probably better accounted for, and it may be, even though it's more complicated, a more comprehensive and better approach to modeling pests than trying to use some adjustment factor that may or may not be accounting for how the pest actually acts, especially if it's limited to an 80 or 100-year time horizon. May not be giving you the best value for your buck in terms of determining a loss factor. If you have more questions about how TAS and TIPSY work, I encourage you to visit the Forest Analysis and Inventory website and look up those two models and see how they perform. And then you can judge for yourself whether OAFs are sufficient to model pest issues in forest stands. Thank you for your attention.